Right, hello everyone. Thanks for the invitation. I'm going to talk about participatory budgeting. This is a paper based on joint work with Kovron and Grzegorz Pieczynski. And what is participatory budgeting? The idea is it's usually done in cities, and the city government allows its residents to vote over how part of the city government's budget is spent. So this is how it might look like. Each voter gets a ballot paper. They get told that the city has allocated, say, 3 million euros to this idea. And then there are lots of project proposals that typically came earlier in the project, and citizens can themselves propose some things, various different things, and they catch with a price tag. And then you're allowed to vote for them. Usually it's some sort of approval voting scheme that there might be a limit on the number of things you can approve, or there might not be. So these are things like improving parks, improving roads, etc. This is a very popular thing. It's now used all over the world. I think the largest is in Paris, where they spend 100 euros per year. And because it is so popular and still growing, if we can make better theory for this voting process, it could really improve the practice around the world. And in addition, the formal model also has other applications. In particular, think of research grant funding. If you're a grant agency, you get lots of research proposals. You need to decide which of them to fund, and you have a panel that gives their recommendations. A very thing. Okay, so to think about how this voting should work and what voting rule we should use, I've drawn this map of a fictional city that I call Circleville. Circleville has 400,000 residents, and conveniently they have $400,000 to spend participatory budgeting. And here you can see all sorts of projects that were proposed in Circleville. Circleville comes in 4 districts: north side, east side, south side, and west side. They have roughly similar populations, though north side is larger. And let's suppose for the moment that all these projects are very popular within their district, but not outside the district. So for example, all the north siders will vote for exactly A and B and C and D, but none of the other projects. Now, if that's the case, we can tally up the votes of the various projects. This is too much for my computer. Okay, here we go. And so the voting rule that's usually used is we sort the projects in order of the number of votes they got, like here, so that's their approval score. And then we start filling the budget in order of number of votes. So first we buy lots of things from north side. So we can afford A, B, C, and D here. So far we've spent $380,000, so we still have some left over. We can afford project F for 10,000 and project I for 4,000. Now we've spent $394,000, and none of the projects is under $6,000, which is what we still left. So this is where the rule stops. Okay, so is this a good outcome? So this is the standard rule that's used, but it doesn't look like a good outcome because we've spent almost all the money in north side. Why did we do it? For a kind of plurality reason. North side is the largest district, so all their projects have the largest number of votes. So we start out here and we ignore everyone else unless there's any budget left over. Right, and that seems intuitively the wrong thing to do. Rather, we want to spend about, say, $120,000 in north side and have about 3/4 of the budget left for the other districts. Cities know this, and so what they do instead is that they split the city into districts and they run completely separate elections in each district. So they would give north side $120,000 and then have north side run their completely separate election where only A, B, C, and D are on the ballot. Right, and east side will have only their project on the ballot. And so this clearly gets around this problem. But it's not clear this is the right thing to do either, because maybe north-siders don't only have preferences over the projects in their district, but also about other projects. So for example, A and T here, they are close to the border of districts. So maybe some west-siders want to vote for A and some north-siders want to vote for T. but they can't do it in these separate district elections. And so we can't actually realize that these projects would be pretty popular. And so they might not get funding, even though they would get funding if we knew all the information. Similarly, C here is in a park, might be a playground. And so parents around the city might want to vote for C. And so that would justify its large price tag. But with district elections, maybe there are not that many parents in Northside, and C would not get funded. Okay. Instead, I'd argue is we want to have proportionality. We want to have participatory budgeting with proportional representation. And the idea of proportional representation would be something like this. Suppose there's a group of 30% of the voters. They have similar interests. Then their interests should be represented by spending of about 30% of the budget. So a fraction of the voters should correspond to a proportional size fraction of the budget. And crucially, a voter could be part of several interest groups. So these groups could be districts, could be just local areas, which could be the district, but could also just be the northwest corner like here, or it could be, say, cyclists who all vote for building a bike path along the river in Circleville. Okay, so now our task is, can we design a rule that on its own finds all of such interest groups and represents all of them proportionally? Okay, that seems difficult. And so let's go to multi-winner voting. I think you've heard a bit about this already, where proportional representation is better understood. And in fact, multi-winner voting committee elections are a special case of participatory budgeting. So suppose we are looking at a country where they have a parliament, say 577 seats. This is the number of seats available in France. Then we can think of a budget of 577 euros. Each project costs €1, and these projects would be the candidates for the committee. And then participatory budgeting is just select 577 of the available candidates. Okay, so the idea, so this is what we call the unit cost assumption. Everything costs the same. And so because of this reduction, we can now look at multi-winner rules and try to get inspiration and hope to generalize multi-winner rules to the more general case of participatory budgeting. So let's remind ourselves of some of the rules that exist. So these will be 3 rules I talk about, but before I do that, I'll need to give you some definitions of various notions of proportionality. And I think you've seen some of them earlier. I've classified them here in order of strength, 1 star, 2 star, 3 star, and 4 star. And for easier notation, I'll just go through them very quickly. Let's assume that the committee size, we have 100 seats available. Right, and let's suppose S is a group of voters. And then the weakest notion here that I call unanimous justified representation says that if S is a group of voters that say consists of 30% of the voters, and they all vote for the same candidates, 30 candidates, so they all have the exact same ballots, and they have at least 30 candidates that they approve on them, then at least 30 seats are filled with candidates they approve. Right, so in this case, S is very clearly an interest group. They have the exact same votes, and then we should give them their proportional number of seats with things that they like. Right, and in these other notions, in these stronger notions, we weaken the idea that S needs to have the exact same votes. So for example, here in proportional justified representation, PJR, it says that if we have a 30% group of voters, and there are at least 30 candidates that they all approve, they might have different ballots, but we can find at least 30 where they all agree. And at least 30 seats need to be filled with candidates that at least one of them approve. So we take the union of their approval sets, and from that union, at least 30 need to be selected. And at EJR, slightly stronger. And the strongest notion is the core. And the core is, of course, taken from cooperative game theory. And for this setting, it would say, suppose we have a group of voters, 30%, then they deserve 30% of the budget. Suppose that they have an idea T of 30 candidates because they deserve 30 candidates. then it cannot be the case that every voter strictly prefers T to S. So to satisfy the core, at least one member of S must prefer the outcome to their own idea T. Okay, so here are 3 voting rules. The utilitarian rule is to suspend them. Just selects the K candidates who have been approved most often. This is essentially the naive rule we've seen run in Circleville. This has nice properties. It's polynomial time for approval preferences, dichotomous preferences. It's strategy proof, but it's completely unproportional. Even very large groups might have 0 representation if there's an even larger group somewhere else that is cohesive. Right, so this I don't think will do. And so let's have a look at Thiele's method and Fragmens method. These are methods proposed in Sweden in the in the 1890s. And they are more proportional. So Thiele's method is also now known as proportional approval voting. It finds a committee that maximizes this magic objective function. This is a sum over the voters, and then a function of the number of candidates in the committee that they approve. It's harmonic numbers, and one can see that only harmonic numbers will give the right outcome. And this is proportional. In fact, it's 3-star proportional and satisfies a very strong proportionality condition, extended justified representation. And in fact, it's an open problem whether 4-star proportional committees, that is the core committees, always exist. And it does come with downsides. In particular, it's NP complete to compute the committee that maximizes this objective, and it's also manipulable. And then there's Fragmens method. It's slightly harder to explain, so I won't explain it here, but the rough idea is that voters can sequentially purchase candidates using virtual money that we give them. And this satisfies 2-star proportionality, so a weaker notion, but it makes it polynomial time computable. Now, with Piotr, I've argued in a recent paper that arguably just saying that Fragmens method satisfies just this 2-star notion is not giving it full justice, and there are several other notions of proportionality that Fragmens satisfies and that Thiele's method actually doesn't satisfy. So this should not deceive us into thinking that Thiele's method is more proportional in every sense than Fragmens method. Okay, so now we want to try to take these ideas and generalize them to participatory budgeting and hope that they work out well. Now, it turns out Thiele's method will fail completely. To see this, let's consider this example of another city. This one's called One Town. They have 90,000 people living there, $90,000 to spend. And One Town comes in 2 districts, left side and right side, with population 60 and 30,000 respectively. And left side has 3 projects, L1, L2, L3, each for $20,000. Right side has a project for $45,000. And if we look at these costs and the available budget, then we find that the maximal budget feasible knapsacks are these 2. We can either buy all the Ls, right? They are affordable for 60,000, but once we've bought all 3 L projects, we cannot then afford the right project. Or else we can afford the right projects, and then we can afford exactly 2 out of the 3 L projects. And now we can calculate the PAV score, so the value of this metric objective function. And we find that this here is preferred by PAV, gives us a higher score. But that's the wrong answer. This output is not proportional. Why not? Because left side has 60 out of 90,000 population, so it should get a proportional amount of the available budget. That is $60,000. With $60,000, they can afford all 3 of their L projects. And so the right side does not deserve the right project. So this fails proportionality for left side.
Sorry?
Yeah.
This example makes one question if proportionality at all is a good notion, because here actually it seems kind of unfair that the right side doesn't get anything at all.
Right.
Oh, it's okay.
Yes. Yeah, well, I also think that it's just a nice sort of on the edge example where it's not completely clear that this is the right conclusion. You could say right side is wrong in that they don't have good ideas for, like, they only have really $30,000 and they haven't come up with anything to do that you can do with only $30,000. And so they've come up with this dream idea, but they just can't afford it. So that would be one way I think of saying that this is the right outcome. But I agree, it's not completely obvious. Okay, let's look at Two Town though. Two Town is a very similar town. In fact, it's extremely similar. It has the same districts, the same population sizes, the same projects, except that the projects now cost different amounts. Now they all cost 30,000. The maximum budget feasible knapsacks have not changed, so we can still either buy all the L projects or 2 L projects and an R project. We can't afford all 4. But now in this case, by the same argument, buying all the L projects is not proportional. Why? Because now right side does deserve its own project. But now what do we have here? We have 2 towns, 2 instances. They are extremely similar. They have the same budget, same population, same district structure, same utilities, same feasible sets. Everything the same. The only thing that's different is the prices of the projects. And the correct answer differs between them. So that means if we do want proportionality, then we need to have a rule that depends on the costs of the projects and not just on this information. So this in particular implies that we can't do any maximization thing. So we can't maximize some objective function that depends on utilities over the collection of feasible sets. It won't allow us to be proportional. And so we haven't come up with any generalization of Thiele's method, PAV, to participatory budgeting that somehow takes into account these costs. It could be that there exists such a generalization, but just maximizing some objective function over the set of feasible knapsacks won't work. But we do have an idea for a rule that does work, and it's more similar to Fragmen's idea. Yeah, here's what I've said as a theorem statement. And so we propose a rule that we've unimaginatively called Rulex, and then we couldn't think of a better name. And now it's published and other people have used that name also. So I think it will stick for the moment. So Rulex is a simple sequential rule. And how does it work? We take the city budget, we split it evenly among residents, and we put each resident's share in a virtual bank account. And then repeatedly until the budget runs out, we look for a project that can be afforded by its supporters. So some people have voted for the project. We look into their bank accounts. We sum up the money they have. If they have enough to pay for the cost of the project, then this project is eligible. And for each of those projects, we look at the cost. We try to divide the cost as evenly as possible among supporters. And then we implement the project where we can do this as evenly as possible and charge them accordingly. So here's this in a more explicit way. So suppose there are several affordable projects, then we take the one where the maximum payment is smallest. So here's an example of a project. It costs $16. Here are the 6 voters that approve it. And the height of the bars are how much money the voter has left in their bank accounts. Voter 6 has no money left at all anymore. And we try to spread this cost of $16 as equally as possible among voters. So this means that voters 1 and 2 spend their entire remaining budget, and voters 3, 4, and 5 each spend $4. And so here we can pay for project 1 with a maximum payment of $4. Here's project 2. Project 2 is the same. It has the same approvers, voters 1 through 6, but it costs less. It costs only $9 rather than $16. And because it costs less, we can spread its cost more evenly in the sense that the maximum payment is smaller, just $2. And so rule X would first buy project 2 rather than project 1. And the idea is cheaper is better. If we can make the same voters just as happy for a smaller cost, then we should do that first. And so this idea of taking the project with the maximum payment smallest implies cheaper is better. It also implies that wealthier supporters is better. So here's a different comparison. Now 2 projects that both cost the same amount, $16, but they are approved by different sets of voters. And project 2 is approved by wealthier voters. Because they are wealthier, we can split the cost of the project more evenly with a maximum payment of just $266 rather than $4. And why is that desirable? Well, a wealthier supporter means an unhappy supporter, because so far we've not been able to spend their money. So we've not been able to put projects that they approve into the committee much. And so they still deserve representation. And so if we have a project with wealthier supporters, that has a better claim to go into the committee. So this is rule X, and rule X, rule X satisfies some strong proportionality notions, in particular a version of extended justified representation. I'm going to give a formal definition soon, but let me just show you how this might look in practice. So I've run rule X on some data from Warsaw. So there's a wonderful website that some people have recently set up called Pabulib, Participatory Budgeting Library, which is similar to Preflip, but for data taken from participatory budgeting elections. So far, this is all Polish data, plus 1 data set from Toulouse. And there you can download voting data, and they have actual approval preferences from people. And so I've taken the 2021 election from this district here of Warsaw. And this is the data. They had 4,000 voters there, 51 project proposals. The budget was 3.8 million zloty. And so the budget per voter is about 900 zloty. So divide by 4 to get sort of euros, dollars. And then you can run rule X on this. And what I find nice is that after you do it, you can tell each voter how their money was spent. And this is a kind of certificate for the voters that their money was spent well. And it's also a certificate of representation. Everyone has been represented. So here's just a random voter that I took and checked how their money was spent. So they had a budget of 934. Is there a question coming?
Yes, sorry. Here, everyone is paying the same taxes, right? It's not that high income people are paying more.
Everyone gets the same amount of money to spend, but
so it's not connected to the taxes that people are actually paying?
No.
Okay, thanks.
Yeah, so everyone has the same claim on the budget, even though the budget will have probably come about with unequal inputs. Though, of course, you can run all this with different entitlements to start out with, and things will generalize. So here's an example. So the personal budget is 934, and here are my Google Translate descriptions of the various projects. It didn't work out well, but you can get a kind of idea what's happened there, and you can see how much money the voter virtually spent on these projects. Here are 4 projects that they approved, but that were not elected. Now, notably, there's some unspent budget here. So we didn't spend the entire budget. This is a bit of a problem. So rule X will often not spend the entire available budget. And this is because even though lots of money is left over, none of the unelected projects has enough supporters or rich enough supporters to pay for it. And this can actually become relatively bad. So here's another voter. They approved only 3 different projects, and that wasn't just not enough. So with those 3 projects, because we split the payment as equally as possible, we spent almost none of their money. And so we had 3.8 million available as the budget, and I think 1.3 million was left over at the end. And there are various ways you can deal with it if you dislike this behavior, and we discuss several in the paper. But maybe it's the right thing, and then you just don't spend the money and let the government do something else or use it next year or something like that. Okay, so here's EJR. This is the property that Rulex satisfies. It says that for every group S of voters who approve L projects in common, and those L projects are affordable with the right fraction of the budget, then there must be a voter in that group who approves at least L candidates in the selected committee. And the proof strategy for this is that because these voters are sort of large enough and they approve things in common, it will be possible to spend most of their money and so make them happy enough. That's roughly how it works. In fact, Rulex, we can extend it to additive utilities. And that seems like a good thing to do because projects often come in very different costs, and just 0-1 utilities, which we assume implicitly before, won't be able to get us preference information that's fine-grained enough. So here's an example from a recent Parisian election where there was both a project for 560,000 euros to refurbish some tennis courts, or a project for 3,000 euros to get some materials for a classroom project. They got essentially the same number of votes. And that doesn't seem right. There's probably more information here. But funnily enough, because of the silly voting rule that everyone uses, because the tennis courts got slightly more votes, this got implemented first, and then there wasn't enough money left over for this 3,000 euro project. Let me briefly mention another rule that we've proposed. So this is EJR. Full justified representation, FJR, here is a stronger notion. It says that suppose you have a group of voters S, they can propose a set T of the appropriate size, and each voter in S gets utility at least, say, L from T. Then there must exist a voter in S who gets utility at least L from the selected committee. One can check this is stronger than EJR, and we have a very simple rule we call the greedy cohesive rule. And what it does is it just repeatedly searches for a group S who still has a claim like this, and then it just implements their claim. So it finds a group S with a maximum L, elects all projects in T, and deletes all of the stuff, and again finds such a group. And this very simple method satisfies FJR. And in fact, it works for any monotone valuation function. So this is not even using additivity or approval. Any monotone valuation function will work. Okay, so I'd like to close by briefly going through some future directions that I think would be interesting. So first, I've given you this, I've briefly mentioned this rule that satisfies this FJR notion, and it shows that it exists for arbitrary monotone valuation. That seems very useful, but this rule has two downsides. It's completely ad hoc, it's not very natural, and it's hard to compute. In fact, it's very hard to compute. So when I tried to run it on this Warsaw data, I waited for 4 hours to see the first project being purchased, and it wasn't enough time. So this is an extremely difficult to compute rule. So it's completely useless in practice. And so the question is, can we give this guarantee in polynomial time or even in reasonable time? And is there a natural such rule? Consider mutually exclusive projects. So assume there's an empty plot of land. There are several project ideas for what we could build there, but we can only build one thing. It's easy to adapt rule X to that, right? Once you've purchased one of the projects that you can do on that plot of land, you're then not allowed in the future to purchase another such project. Or it's easy to adapt various axioms, but rule X then won't satisfy those axioms anymore. So there's a question of whether we can, in this setting, still guarantee proportional representation. This is related to the literature on public decision-making, which is a particular model with additive valuations. as well as committee elections with variable number of winners. And there's some existing very recent work on this, but it only looks at very special cases or looks at computational questions rather than proportional representation. Here's another one, divisible projects. So suppose that some projects can take an arbitrary amount of funding. So at the moment, we're looking at projects that are all or nothing. But some projects can quite easily scale up. So for example, how much should we spend this year on fixing potholes in the street? And this is essentially divisible, essentially completely flexible. It's just how many number of hours do we buy from the contractors doing it. And again, we can easily incorporate this into the existing model by introducing, say, lots of projects at $1 each. And in particular, this also fixes this issue where Rulex doesn't spend the entire budget. So if we have such divisible projects, they can eat up all the budget very easily, provided that the voters all approve at least one of these flexible projects. But here's a problem. So we know, I think Marcus talked about this, about party approval and approval-based apportionment, where we also have these projects or the candidates that can be copied. And we saw in that situation that PAV is actually the best rule. In particular, PAV satisfies the call, and it intuitively does the correct thing for the setting. And in fact, Rulex behaves quite weirdly in the presence of these types of projects. So one way of seeing is to consider two parties, A and B, right? And so these parties both come with as many candidates as you like to elect from them. Say 20% of voters approve both parties, but of the rest, 60% approve A and 40% approve B. In this case, PAV does the following. It gives 60% of the seats to A and 40% of the seat to B, which seems right. But Rulex is sort of thrown off track by the voters who approve both and actually gives 68% to A and 32% to B. And this doesn't violate any of the axioms that we've said Rulex does satisfy, but it does seem wrong. But so now we're in a bit of a problem where we know that PAV from our one-town, two-town example doesn't really work for budgeting, but it seems like the best thing if there are only these copyable projects. So this leaves the question of whether we can somehow combine the ideas here, or maybe there's even a third completely different type of rule that does it. Here's a very similar idea of projects with milestones, but I don't think I'll go through that in detail. Okay, that's all I had to say. Thanks for your attention. Thanks.
Okay, great. Thank you very much. I think we can thank this. Yeah, I have mic. It's working, right? So thank you very much. We can thank the speaker. And there are some questions. Nizar, would you voice yourself?
Sure. Great talk, Dominik. Yeah, so one question I have was regarding this issue about unspent budget in Rulex. And I was thinking that if we want some kind of fairness over time, so for example, if we want to satisfy some notion like the core or EJR, but kind of across many years, then it may be possible to show that you cannot select a maximal budget feasible set of projects every year individually. Because then basically you would almost be kind of, if you don't have enough budget rolling over to the next year, then the voters that you weren't able to be fair to this year, you cannot kind of compensate for them the next year. And if we can show that, then that could be a good justification for kind of not fixing this issue of Rulex and rather kind of actually rolling over the budget to next year. So do you know, have you thought about this deduction?
I haven't, but thinking about it right now, it does seem that there are almost certainly such examples. So think of exactly this divisible project thing. Suppose pothole fixing gives us positive utility, but extremely small. And we do have, every couple of years, we have an idea for a massive project that we can't afford in any single given year, but gives us very high utility. Then the fairness notion over time will say that eventually we should get such a big project approved, but we will actually spend all our money on pothole fixing always. So this argument does require non-approval utilities, probably. But interesting whether one could try to do it with approvals.
Yeah, and also it would be nice to have an example where in any given year, the projects that are proposed are only of like cost that's less than equal to the budget of that year.
Right.
And still somehow this issue appears. So very nice. Thanks.
Interesting. Thanks.
Okay, more questions? The audience? Yeah, please, Hervé.
Yes, Dominik, I did not understand exactly when you mentioned the divisible projects, when you said that you're going to cut them into pieces of $1. So what do I do if I approve? I mean, I approve this very expensive project. Shouldn't I then approve any little brick of $1 on that project, or am I supposed to reveal a kind of a cardinal utility by saying I approve 75 out of 100 little pieces of $1? What do you mean there? In the context of approval voting, it seems to me you have to approve everything or nothing. I mean, maybe I misunderstood.
Yeah, that's right. Actually, the problem is even worse, because if you approve things, we interpret your utility as being the number of projects that you approved and that were funded. So if you like the epsilon size of each of the small projects makes a big difference, because you become much happier if we select 1,000 thousandths. But so yes, so this kind of assumes that you take cardinal additive valuations.
But is there actually in practice, are there cases in practice where the city, for instance, imposes a maximal budget that you can approve, which is smaller than the entire proposal budget? See, like saying you can approve up to 1 million zloty, but because they know that they want to do a subset and they just want to hear choices. Have you seen any instances of that being done? Or?
So there's the idea of what's called knapsack voting, where you're only allowed to approve things that cost as much as the overall budget. And I think they've done that in a few US cities, but it's not so popular in the theoretical literature.
It wouldn't change too much what you are doing, I think. Or...
No.
I mean, it would simply restrict your strategies, but not in a dramatic way. Yeah. Okay, thank you.
Thank you.
Okay, one more question.
Marcus says.
Okay, then.
Can I ask a question?
Yeah, please.
Okay. Very nice talk. I have also kind of more practical question. If you talk about this additive utility setting, I mean, how would you elicit such preferences in practice, and also maybe would you scale these preferences all, that they are all kind of the same maximum utility? Would this it would make a difference, I suppose? Would it make sense to scale them?
Yeah. So our rule does like very naughty comparisons of utilities. So if you give very high utilities, that makes a big difference. So you probably in practice want to scale things. Of course, the rule is kind of, it takes the valuations we're given as true, and then there's a good thing with that. So if you have like a good elicitation scheme to get the true valuations, like do quadratic voting or something like this, perhaps even, then it's good. Whether you can just use it out of the box is unclear.